Hello and welcome. In this video, we will explore the differentiation of several important classes of functions that are fundamental to the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to, first, differentiate logarithmic functions with any base. Second, differentiate the 6 trigonometric functions: sine, cosine, tangent, cosecant, secant, and cotangent. And third, differentiate the inverse trigonometric functions: arcsine, arcos, and arctan. We will derive these rules and apply them through a series of worked examples, focusing on the techniques required for HL-level problems. Let's begin with logarithmic functions. Our goal here is to differentiate functions of the form log base a of x. We want to find the derivative of y equals log base a of x. To do this, we'll use the change of base formula to convert the logarithm to base e, the natural logarithm, which we already know how to differentiate. The change of base formula states that log base a of x is equal to the natural log of x divided by the natural log of a. So our function becomes y equals ln x over ln a. Notice that ln a is a constant. We can rewrite this as 1 over ln a times ln x. Now we can differentiate this using the constant multiple rule. The derivative dx is the constant 1 over ln a times the derivative of ln at x, which is 1 over x. This gives us our general rule. The derivative of log base a of x is 1 over x times ln a. Let's apply this with a couple of examples. First, let's find the derivative of f of x equals log base 2 of x. Using our formula, the derivative f prime of x is 1 over x times the natural log of 2. It's as simple as that. Now for a more complex example involving the chain rule. Let's differentiate y equals log base 5 of the quantity 4x squared plus 3x. Here, our x in the formula is replaced by the function 4x squared plus 3x, so we must use the chain rule. The chain rule states that the derivative is the derivative of the outer function, evaluated at the inner function, times the derivative of the inner function. The derivative of the outer function, log base 5 of u, is 1 over u times ln 5. The derivative of the inner function, 4x squared plus 3x, is 8x plus 3. Substituting u back, we get 1 over the quantity 4x squared plus 3x times ln 5, all multiplied by 8x plus 3. This simplifies to 8x plus 3, all over the quantity 4x squared plus 3x times ln 5. So we have successfully differentiated logarithmic functions with any base, using the change of base formula and the chain rule. Next, let's turn our attention to the derivatives of trigonometric functions. We'll start with sine and cosine. Our objective is to find the derivatives of y equals sin x and y equals cosec. We can visualize these derivatives by looking at the graphs. The derivative of a function at any point is the gradient of the tangent line at that point. Here we have the graph of y equals sin x. Let's consider its gradient. At x equals 0, the tangent is horizontal, so the gradient is 1. At x equals pi over 2, the tangent is horizontal, so the gradient is 0. At x equals pi, the gradient is 1. And at x equals 3 pi over 2, the gradient is 0. If we plot these gradient values, we see they perfectly match the graph of y equals cos x. This suggests that the derivative of sin x is cos x. We can do the same for y equals cosine. At x equals 0, the gradient is 0. At x equals pi over 2, the gradient is 1. At x equals pi, the gradient is 0. And at x equals 3 pi over 2, the gradient is 1. Plotting these points reveals the graph of y equals negative sin x. So, the derivative of cos x is negative sin x. These results can be formally proven using the first principles definition of the derivative and trigonometric identities. For the IB/HL course, you should be familiar with these proofs. The key results are: the derivative of sin x is cos x, and the derivative of cos x is negative sin x. Now, let's find the derivative of tan x. We can use the quotient rule. We know that tan x is sin x divided by cosc. Let u equal sin x and v equal cos. Then u prime is cos x and v prime is negative sin x. Applying the quotient rule, u prime v minus uv prime all over v squared, we get cos x times cos x minus sin, x times negative sin x all over cos squared x. This simplifies to cos squared x plus sin squared x all over cos squared x. Using the Pythagorean identity, cos squared x plus sin squared x equals 1. We get 1 over cos squared x, which is secant squared x. So the derivative of tan x is secant squared x. We have now established the derivatives for the three primary trigonometric functions. Now, let's extend these results using the chain rule. This is crucial for differentiating composite trigonometric functions. Our objective is to differentiate functions of the form sin of f of x, cos of f of x, and tan of f of x. Let's consider y equals sin of f of x. We can use the substitution u equals f of x. This gives us y equals sin u. By the chain rule, di will dash dx is d do times do dx. The derivative of sin u with respect to u is cos u. The derivative of u with respect to x is f prime of x. Substituting back, we get cos of f of x times f prime of x. We can apply the same logic to cosine and tangent. This gives us the general chain rule for trigonometric functions. The derivative of sin of f of x is cos of f of x times f prime of x. The derivative of cos of f of x is negative sin of f of x times f prime of x. And the derivative of tan of f of x is secant squared of f of x times f prime of x. Let's work through an example that combines the chain rule with the product rule. Consider the function y equals x times sin of x squared. This is a product of two functions, x and sin of x squared, so we must use the product rule. The product rule states that the derivative is u prime v plus u v prime. Let u equal x and v equal sin of x squared. The derivative of u is 1. For v prime, we need the chain rule. The derivative of sin of x squared is cos of x squared times the derivative of x squared, which is 2x. So, v prime is 2x cos of x squared. Now we substitute these into the product rule. We get 1 times sin of x squared plus x times 2x cos of x squared. This simplifies to sin of x squared plus 2x squared cos of x squared. This example demonstrates how to combine multiple differentiation rules. Let's now look at the derivatives of the reciprocal trigonometric functions: cosecant, secant, and cotangent. Our objective is to find the derivatives of cosec x, sec x, and cot s. We can derive these using the quotient rule or the chain rule by expressing them in terms of sine and cosine. Let's start with cosec x, which is 1 over sin x. We can write this as sin x to the power of negative 1. Now we use the chain rule. The outer function is u to the power of negative 1, and the inner function is sin x. The derivative is negative 1 times sin x to the power of negative 2, times the derivative of sin x, which is cos x. Rewriting this, we get negative cos x over sin squared x. We can split this into negative cos x over sin x times 1 over sin x. This simplifies to negative cot x times cosec x. So, the derivative of cosec x is negative cosec x cot x. Using a similar process, we can find the derivatives of secant and cotangent. The derivative of SECA is sec x tan x, and the derivative of cot x is negative cosec squared x. Let's work through an example that combines these with the chain rule. Let's differentiate e equals 8 cotangent cubed of x over 2. This requires a triple chain rule. We can think of it as 8 times u cubed, where u is cotangent of v and v is x over 2. The derivative is 8 times 3 times cotangent squared of x over 2, times the derivative of cotangent of x over 2, times the derivative of x over 2. The derivative of cotangent of x over 2 is negative cosecant squared of x over 2 times 1/2. The derivative of x over 2 is 1/2. Multiplying everything together, we get negative 6 cotangent squared of x over 2, cosecant squared of x over 2. This example shows the power of the chain rule for complex compositions of functions. Finally, let's explore the derivatives of inverse trigonometric functions. These are often called arcsin, arcos, and arctan. Our objective is to find the derivatives of arcsin x, arcos x, and arctan x. We will use a technique called implicit differentiation. Let's start with y equals arcsin x. If y equals arcsin x, then by definition of an inverse function, x equals sin y. Now, we differentiate both sides with respect to y. The derivative of x with respect to y is dx sur I. The derivative of sin y with respect to y is cos y. We want di dx, which is the reciprocal of dx di. So, di dx equals 1 over cos y. We need to express this in terms of x. We can use the Pythagorean identity. We know that sin squared y plus cos squared y equals 1. Rearranging for cos y, we get cos y equals the square root of 1 minus sin squared y. Since x equals sin y, we can substitute x for sin y. This gives us cos y equals the square root of 1 minus x squared. Substituting this back into our expression for di dx, we find that the derivative of arcsin x is 1 over the square root of 1 minus x squared. Using the same method, we can find the derivatives for arccos x and arctan x. The derivative of arccos x is negative 1 over the square root of 1 minus x squared. And the derivative of arctan x is 1 over 1 plus x squared. Let's see an example with the chain rule. Let's differentiate e equals arctan of x squared. Here, our x in the formula is replaced by x squared. We use the chain rule. The derivative is 1 over 1 plus the inner function squared times the derivative of the inner function. This gives us 1 over 1 plus x to the fourth times 2x. The final answer is 2x over 1 plus x to the fourth. Let's now tackle a more complex problem that requires combining several of these rules. This is the type of question you might see in an IBHL exam. Consider the function f of x equals the natural log of the square root of secant of x squared. Before we differentiate, we can simplify this expression using logarithm properties. This will make the differentiation much easier. First, we can write the square root as a power of 1/2. Then, using the power rule for logarithms, we can bring the 1/2 to the front. Now, we need to differentiate 1/2 times the natural log of secant of x squared. This is a chain rule problem. The derivative f prime of x is 1/2 times the derivative of the natural log of secant of x squared. The derivative of ln of u is 1 over u times u prime. Here u is secant of x squared. So we have 1/2 times 1 over secant of x squared times the derivative of secant of x squared. Now we need to find the derivative of secant of x squared. This is another chain rule. The derivative of secant of u is secant u tangent u times u prime. Here u is x squared. The derivative of x squared is 2x. So the derivative of secant of x squared is 2x secant of x squared tangent of x squared. Let's substitute this back into our expression for f prime of x. We get 1/2 times 1 over secant of x squared times 2x secant of x squared tangent of x squared. Notice that the secant of x squared terms cancel out, and the 1/2 cancels with the 2x. This leaves us with a surprisingly simple result. F prime of x equals x tangent of x squared. This problem highlights the importance of simplifying expressions before differentiating and carefully applying the chain rule multiple times. Let's conclude with a recap of the key differentiation rules we've covered today. We started with the derivative of a general logarithmic function, log base a of x, which is 1 over x ln a. Then we covered the 6 trigonometric functions. The derivatives are cos x, negative sin x, secant squared x, negative cosecant x cotangent x, secant x tangent x, and negative cosecant squared x. Finally, we derived the derivatives of the inverse trigonometric functions. 1 over the square root of 1 minus x squared for arcsin x, negative 1 over the square root of 1 minus x squared for arccos x, and 1 over 1 plus x squared for arctan x. Remember that the chain rule is your most powerful tool for differentiating composite functions, and it can be applied multiple times in a single problem. Also, don't forget to simplify expressions using logarithm and trigonometric identities before differentiating. You are now equipped to differentiate a wide range of logarithmic and trigonometric functions, a key skill for the IBHL exam. To solidify your understanding, here are 5 practice questions in the style of the IBHL exam. Pause the video.